All right, good morning, fellows alumni. Welcome to the High Performance Computing Workshop. This is track 1. So to be clear, this is the track targeted at incoming first year and second year fellows and cover some introductory topics to help to familiarize you with high performance computing, or HPC. So each speaker will talk for an hour, and then we will have an HPC facility panel presentation in this room. At the end of the HPC workshop, both the talks and the panel, there will be a buffet, sandwich, salad, lunch, with also grab-and-go options if you guys need to make a flight soon afternoon. I will now introduce the first speaker, who is Rob Neely from Lawrence Livermore National Laboratory. Rob Neely is a Lawrence Livermore National Laboratory computations employee with over 20 years of experience in high-performance computing and scientific software development. Rob is an Associate Division Leader at the Center of Applied Scientific Computing, or CASC, and leads the Advanced Architecture Software Development Project at Lawrence Livermore National Laboratory. In that role, he is charged with coordinating application software activities with the Advanced Scientific and Computing, or ASC, program to prepare for the new and challenging era of exascale computing. Rob also works with the ASCII program office centered in Livermore Computing, where he is actively involved in next-generation platform procurements, co-design activities, and long-term strategic directions for exascale computing at Lawrence Livermore National Laboratory, the Department of Energy, and the nation. So with that, I'll turn the time over to Rob.
Okay, thanks. Okay, can you hear me okay? Sounds like I'm mic'd up. So I can't hear very well. I flew with a cold this week, and my head is right now clogged up with fluid. So if you have a question, just make sure to speak loudly, or I'll ask Britton to help me with that. What I'm going to talk about today, I'm going to give you a little bit of a background of high-performance computing throughout time. I'm going to go through that pretty quickly, but I wanted to give you sort of set the stage for where we're at today, which is, if you've heard people talking about this advent of exascale computing, that's really a moniker for some big challenges we're seeing, both in how we design platforms and then how applications get mapped to those. I'm going to assume not too much deep knowledge about computing, so I'll talk about some basic terminology, words that you're going to need to understand to interact with some of the applications folks and hardware folks in HPC. And then I'll talk a little bit about, just touch briefly on things like programming models, which are, okay, now you've got this architecture with all these complex features, how do you map an application onto that? And hang on, there's a lot of material here, so we'll see if we can get through it all in 60 minutes. So this chart here is starting on the x-axis in 1952 through about a year or so ago. You know, what are all the top machines in the world? And this isn't all of them. This is a little bit slanted toward some of the machines in the NNSA on the DOE side. But the point I want to make here is that there's been really, thus far, 3 major eras of computing. And I'm going to go through each of these and talk a little bit about the characteristics of each. The thing that's, the reason I'm making this point is we're on the cusp of a new era in computing here, where things are really changing dramatically out from under us. And really, we don't quite know what to call this yet. There's no one defining feature necessarily of this new era like there has been in the past. You know, we had mainframes, we had vectors, we had this distributed memory era, which we're still in. But this many-core era, for lack of a better term, is where we're at now. And this is things like accelerators, lots and lots of small, simple cores. It's really all about extracting parallelism from your applications. And I'll point out that if you notice, this curve actually bent upward a little bit in this last era. And this was all due to the ability for us to scale out machines, add more and more processors to these architectures, instead of just relying on single processor performance increases, things like Moore's Law that you've heard of that I'll talk a little bit more about. So we've gotten, the last 20 years really, we've gotten spoiled a little bit by the acceleration in capabilities in high performance computing. And unless we do something very smart very soon, we're gonna lose that acceleration. The reason this is important, to get scientific discovery through computation, you really need 2 different things. One, the application developers out there need some stability in the platforms that they're targeting, and I call that programming model stability. And then obviously you want regular advances in your computational power. It's those two things together that drive scientific discovery, and DOE has really been important in helping manage these transitions and will be critical in this next transition as well. So I'm going to step into a quick history lesson here. Got about 10 slides or so on this. This is just for your information. You don't have to remember all this, but computing goes back, believe it or not, all the way to the 1830s. If you've heard of a guy named Charles Babbage, he actually conceived of this idea of something called a difference engine, which was really the first computer. It never got built, but it was the idea that you could use a machine to do calculations, and Ada Lovelace was his partner and really the first programmer. And that's probably the last time we ever had 50% of the computer science workforce is female, but anyway, in the 1930s, theoretical computing took off with a man named Alan Turing, developed a Turing machine. If you ever take a theory of computations class, you'll learn all about some of the things that he conceived of. It was the 1940s with a machine called the ENIAC that we really had the first electronic computer, the first demonstrable computer, and then later, a man named John von Neumann, who was on loan to Los Alamos, helped improve on that design and really came up with the architecture that formed the basis for the mainframe era that followed. And it was really, as with most innovations, it was defense and World War II that was driving the technology here. It was ballistics projections that they wanted to do these, build these computers for. So throughout the 1950s, early 60s, there was a series of these mainframe computers, a lot of innovation in hardware at this time, a lot of it driven by IBM. I won't go through these in detail, but new memory systems, new ways of thinking about how to port from one machine to the next. Transistors came along, replaced vacuum tubes. At Livermore, UNIVAC came out with a machine called the LARC. This was actually co-designed, laboratory scientists sitting hand in hand with the engineers at UNIVAC to help design these systems. And then going into the 60s, sort of a competitor to the LARC machine was the IBM Stretch. That was at Los Alamos Laboratory. And then a company called CDC came along and really dominated scientific computing, mainframe computers used for scientific computing in that era. And I just point this out because this is a place where a guy named Seymour Craig got his first experience, and he really became seminal in designing supercomputing up through the late 80s. So CDC, Controlled Data Corporation, was the name of the company. They kind of, like I said, led the way. A machine called the 6600, people refer to that just by its name. Remember the 6600? It was really considered the first real supercomputer in the mid-60s, and then the 7600 followed that, and it had an unprecedented run of 6 or 7 years where it was the fastest machine on the planet for a long time. And so this mainframe era, it was really the same machines that people were using for scientific computing were the ones being used for business. That's why IBM was big in this place. It was a very intimate style of programming with the machine. You really had to understand the hardware. Things like compilers and operating systems were being invented as we go. Networking, batch environments, all the things that we take for granted today on machines were really fleshed out in this era. And the US largely stood alone in this era, dominating the HPC market. We now switch to something I'm going to call the vector era. And if you understand what a vector machine is, then, well, I'll explain what a vector machine is in a few minutes. But CDC was the first company to design one of these machines. It was ironically not invented by Seymour Cray. He had left and started his own company at the time and released this machine called the Cray 1, which really sort of set the stage for the vector computing era. I'll note that sort of in the middle here, while all these vector machines were coming out, the University of Illinois and Burroughs developed a machine called the Iliac 4, and that was really a first demonstration of the power of parallel computing. And you know, that really portended the future. You'll see as we get into the next era that parallelism was where it was at. So, question? I'm sorry, I can't.
The question is, what is a vector machine?
Oh, what is a vector machine? I'll talk about that in a minute. I'm sorry, my hearing is completely shot. So I'll get to that in a second. You know, Cray, there were a couple different Cray companies here. There was another design, well, actually, this is still the same Cray company, but another designer named Steve Chen developed a machine called the, whoops, what did I do? Called the XMP. And then there were a series of other Cray machines up through really the mid-90s. And this is when the vector era really ran out of steam. It was becoming too expensive to design these custom machines. So to answer your question, what is a vector machine? It's really the idea that, you know, in scientific computing, a lot of our calculations, equations are laid out in arrays of data. And you've got a loop. You know, I'm going to go from 0 to 1,000 over my particles or my elements or whatever, and I'm going to do some common calculation on each of those. The idea of a vector machine is that if you can load that data up into these long vector registers, then you can chunk that through a specialized piece of hardware called a vector CPU and get an answer out basically every cycle instead of the normal, you know, 10 to 50 cycle latency that you would have. Because remember, the basic way a machine works is you go out, you grab something from memory, you bring it into the CPU, you crank on it, you store the result, then you go on to the next one. The more you can overlap that, the faster you're going to be able to increase your throughput. And vector machines were all about basically optimizing that overlap. The problem with vectorized computing is, you know, if you've got a loop dependency here, this is just a simple example of calculating the Fibonacci sequence. You know, to calculate the value at index I, you need to know the previous two values. It's very hard to pipeline those answers. So there are problems with this vector model. It's not for all algorithms. For some things, it works very well. And in some cases, you got, you know, really incredible speed ups out of these machines. Other things that make vectorization hard, you know, conditional statements, if, then, else type statements inside a loop. If you're not striding regularly through memory, if you're skipping through, say, some kind of index set, I/O calls, function calls, all these things can stymie vectorization. And a lot of this got improved over time through better compiler development. Compilers became increasingly sophisticated during this time. There was always a hope that we could just automatically parallelize code, but the fact is you still had to go in and through things called directives, which if you're a C or C++ programmer are like pragma statements, similar to OpenMP. You had to put hints in your code to say, by the way, compiler, you know, make some assumptions about this loop here, that these arrays don't overlap, or that there's no dependencies in these index sets. And then the compiler could go ahead and vectorize that code for you. So if you could get vector performance, then you could see anywhere, you know, tens of speed up in your code over the serial counterpart. You know, vectorization lives on today in a much smaller form through things like, you know, AVX instructions on an Intel machine. ARM has something called Neon. The PowerPC architecture has something called QPX. So this concept still lives on, but it's not as much the basis for getting performance as it was in this era. Now this is where I think things got interesting. Maybe that's because that's when I was your age, we were going through this shift in computing. But around the late 80s, we began to see a pretty heavy influence from the RISC processor market. RISC stands for Reduced Instruction Set Computer. There were a number of different CPUs out there. Sun had one called the Spark. There was an Alpha architecture by Digital Equipment Corporation, MIPS, PowerPC. All of these were basically on a chip starting to impinge on the performance of these smaller mainframe supercomputers and really driving those out of the marketplace, while at the same time you could begin to strap a number of these together on an interconnect and drive out the high-end market. So the influence that the RISC processor had on both the low-end and the high-end market was pretty intense in the late 80s and early 90s. And this revolution was really driven largely by both cost and scaling. Cost in that you could now, for the cost of a commodity processor used in the emerging PC market, for example, begin to get some of the performance that you used to have to buy a large CDC mini mainframe. And then the companies like SGI, which used to be called Silicon Graphics, they began to develop little machines that would sit on your desktop that, again, could do the work of these large mainframe computers. And then again, by scaling these things out, putting them on an interconnect, there was an explosion of companies coming along and developing these parallel computers. And I just list a whole bunch here. There's probably some I'm missing. A lot of these companies have long since either been swallowed up by their bigger competitors, merged, or just died away. But there was a huge amount of innovation in parallel computing at that time. Another thing that happened is that commodity Ethernet, which is sort of the standard networking protocol used for department workstations and the like, and this thing called Linux came along. And now anybody, basically with full commodity parts, could strap together a number of PCs on commodity Ethernet, run free Linux, and build a supercomputer. So like universities all of a sudden could get into the supercomputing game and through parallel computing. And by the 2000s or so, a lot of these companies, like I said, had died away. Commensurate with this, there was a program called ASCII. Now you'll hear it called ASC, just ASC, which is Advanced Scientific Computations. I can't even remember now. But at the time, it was the Accelerated Strategic Computing Initiative. And it was a 10-year initiative. Remember back on my first chart, we showed that we really bent the curve up and accelerated the growth in computing. That's what the ASCII program was really all about. And it was driven by the weapons labs in DOE to replace underground nuclear testing with this science-based stockpile stewardship. And to this day, that's still the primary mission of the NNSA labs. Interestingly, the Japanese kind of stayed the course with this vector architecture, and to some extent they're still doing that today. They continued to build these custom CPUs designed for scientific computing. They had a lot of help from their government. They developed a machine called the Earth Simulator, and I think it was 2002, 2003, somewhere in there. That really shook up the US market because we had begun going down this path of parallel computing is the way to high performance, and the Japanese came along with this machine, very different kind of architecture based on, where we had quite a bit of expertise from the past. Just as an aside, that was quite a little bit of a scare for the US HPC market at the time. And as a result of that, the leadership computing facilities at Argonne and Oak Ridge were launched around that time largely to help make sure the US stayed on top of the world in HPC. And as you guys probably know, or you'll hear later today, some of the top machines in the world are housed at Oak Ridge and Argonne right now. So this distributed computing era that I talked about, scaling out of largely commodity type processors, we've had a stable programming model called message passing. Initially, this was in a library called PVM, Parallel Virtual Machine, that a lot of people used. It was for the first time you could write one code with one set of library calls to do this message passing, communicating between processors. And if you don't know what I mean by message passing, I'll touch on that in a little bit. But MPI came along around 1995 or so and really solidified that standard. And then there was a real explosion of people jumping onto this programming model, and it's given us this 15 years or so of, probably 20 years by now, of stability in the programming model. And a lot of this, again, the reason I'm telling you all this is a lot of this is ending. We're going to have to start thinking about new ways to program these machines for reasons I'll talk about. So just in summary here, as we were transitioning from these different eras, as we went from the mainframe to the vector era, there it really became about vector machines being specialized for scientific computing, take advantage of these array-based calculations versus maybe transaction-based calculations that you'd see in a large database. That was suitable for the standard IBM type mainframes of the time, but vectors were really dialed in well for scientific computing. As we went from this vector to the distributed memory era, there it was really about scaling out, low cost, improving performance through commodity hardware and the like. Where we're at now is we're moving into this many-core era, which I'm going to talk about a little bit more. The reason that we can't just keep bending that curve up and building bigger and bigger machines and going more and more parallel, it's really about power. The amount of power that these machines take to run are approaching, the kind of thing where you need a nuclear power plant next to you to run them. They're getting really huge. And to build an exascale machine, which is an exaflop of computing, just think of it as about 50 times faster than the current machines that we have at Oak Ridge and Livermore, for example. Using today's technology, that would take something on the order of 100 to 200 megawatts of energy. The reason that's important is a megawatt costs you about $1 million a year in your power bill. So if you're spending more on power to run your machine than you did actually buying the machine, there's a little bit of a problem there. So power is really what's driving this next era that I'll get into a little bit. So let me step back now. I'm going to talk a little bit about the basic architectural features of a large-scale supercomputer. So a supercomputer still takes up a room. They're not small by any stretch. They're made up of these racks. Each rack has a number of what's usually called blades that if you pull out a drawer looks something like this. And this is really going to look pretty similar to what you'd see in a high-end PC or something like that. You've got CPUs and memory and perhaps an accelerator card. This is a cartoon version of that. The fundamental unit of a supercomputer is called a node. And it used to be that a node and a processor were almost one and the same. But these days, people are familiar, if you buy a PC, it's like a dual core or a 4-core processor. More and more, a single processor will have multiple cores in it. And I'll talk about why that's important coming up, or why that happened. I'll talk about that in a little bit. But so a node is made up of basically one or more processors. Each processor sits in a socket. There's usually some common memory that all those processors will share. You may have, usually not often, but you may have some local file system, local disk on there. And increasingly, you're seeing these accelerator cards, things like GPUs, which are graphical processing units. So you may have an NVIDIA card, for example, on your node to help accelerate portions of your computation. Then a node has a way to get out and send message on this network interface. And let's see, I've got a slide coming up on what these interconnects look like. So there's two basic ways to get at parallelism. You can have what's called shared memory or distributed memory architectures. And it used to be that it was kind of one or the other. These days, it's really a combination of both. But in the shared memory computing model, you've got something like this. You've got a common memory system with a bunch of processors, could be 2, could be 100, sharing that same memory space. And if you're breaking your calculation up into pieces to run them in parallel, that's basically how you have to do this. I think Judy will probably talk a little bit about this. But you're breaking your calculation up to run in parallel. Each of these processors will be working on a chunk of it. But at some point, depending on your algorithm, there's going to need to be communication. For example, at boundary conditions of the mesh, or if a particle moves from one location to another. On a shared memory system, that communication is all done through a common address space. So one processor may write to a place in memory, another processor goes and just reads that out of memory. It's a very conceptually simple model to program to, but the devil are in the details. There's a lot of coordination that has to go on when you're using shared memory programming, or threads, it's sometimes called, to make sure that you don't have what's called race conditions, for example, where one processor may assume that a value in memory has been updated, but the other processor hasn't yet. So you have to coordinate a lot of things to do this sort of communication, but it's very fast because it's just over a memory bus that you're doing this communication. The other dominant way of getting at parallelism is this distributed memory model, which is this cartoon down here shows. And it's really the idea that you've got a processor with its own memory space, so its own address space that other processors can't see, and they're connected together through an interconnect or a network. Could be Ethernet, could be something much more sophisticated. But there, if you want to do the communication required to coordinate a parallel algorithm, it's an explicit message that you have to send. So the one processor says, I'm going to send you this data. The other processor says, okay, I'm ready to receive it. When he receives it, he puts it into his memory location. The computation can move on. So these are the two basic models, shared memory and distributed memory, that you'll see. And the fact is that most machines today are really hybrids of this. Nodes, because of this multi-core CPU architectures that are emerging, nodes typically have a number of cores or processors sharing the same memory bus, but then there's an interconnect connecting the nodes together to do message passing. So I've mentioned interconnect. Interconnect is just a fancy word for your network. You need very high-speed networks on a supercomputer to do this communication, to coordinate your algorithms. Some of the interconnects you'll hear talked about, in the old days, there were things like hypercubes. It could be a 3D hypercube or a 4D hypercube. Without going into details, it's just a way of how do you lay out the switches in the network so that you can minimize the amount of time it takes any two processors to communicate with each other. And the idea of a hypercube is that the number of hops that a message has to take to get from any one processor to another scales logarithmically with the number of nodes in the machine. But it's difficult to scale that architecture out, and I'll talk about what I mean by scaling in a minute. There's multi-dimensional toruses, 3D torus, for example. Just think of laying out your processors, physically laying them out in like a 3D grid, and each processor has a wire connecting it to its nearest neighbor. And the torus just basically means that at the ends there's a wraparound wire. Blue Gene, for example, is a 5-dimensional torus, which I can't even begin to fathom how to draw a picture of that, but it's actually a very effective interconnect for large-scale machines. Dragonfly is an interconnect you'll hear a lot of new architectures talking about. The Cray Aries architecture, for example, is a Dragonfly. The NERSC machine is built on this. And Fat Tree has been kind of the standard interconnect topology for a long time. Infiniband is a type of networking that typically uses fat trees, for example. And the idea of a fat tree is that you've got a hierarchical set of switches where the amount of bandwidth as you go up in this tree doubles or scales with the number of nodes that you've got, so that the amount of aggregate bandwidth between any two nodes in the system is constant. And there's a number of challenges in interconnect design that a lot of people are tackling these days. Things like topology mapping. How can I lay my job onto this physical interconnect to try to minimize the amount of communication distance that I'm having to travel, because the speed of light is starting to come into play in some of these designs. But you want to try to make sure that you're using that interconnect as little as possible, because it's not necessarily helping further the computational workload of your problem when you've got messages flying around. So I've used the term scalability a few times. Let me just take a step back and tell you what I mean by that. Scalability is just the term that means the ability of either a piece of hardware or an application to increase its performance potential commensurate with the amount of resources it has. So on the hardware side, can I double the size of my machine and not have to pay 10 times as much for my interconnect by adding a whole bunch of extra switches, for example? On the software side, can I run my program on twice as many processors and perhaps compute it in half the time? That would be ideal scalability. So I'll talk about this a little bit in a little bit more detail, but that's the crux of it, that a piece of hardware or an algorithm that's scalable has this feature that it can grow without running into some bottleneck that maybe is an exponential or even a logarithmic type scaling problem. And most most algorithms, have some sort of scaling limits in it. A lot of the work that's been done to port to machines like Mira, which is the Blue Gene machine, has been, there's not a lot of memory on one of those cores. And so if you've got a data structure that scales with the number of processors in your problem, that can begin to take up a large chunk of memory on one of those distributed memory nodes. So the kind of work that people are doing to port algorithms to these bigger machines, it's not always about just, is my performance scalable? It's also, are my memory and my data structures that I use in my program scalable as well? There's two primary kinds of scalability people talk about: strong scaling and weak scaling. And I wish I had a simple way to tell you how to remember which is which, but I don't. There's no sense to why one is called strong or weak scaling to me anyway. So you'll just have to remember that in a strong scaling study, and again, this is the idea that I'm running my problem, maybe on one processor, 10 processors, 100 processors, and I want to understand how it scales. If I'm doing a strong scaling problem, I'm keeping my overall problem size fixed, and as I add processors, I want my time to solution to get lower. That's strong scaling. And if you plotted that on a logarithmic chart here with time on this axis and the number of processors out here, if it's logarithmic, you'll see a nice -1 slope that's your ideal scaling. Now, if your code or application doesn't scale well, what you'll see is that you add more and more processors to it, the time to solution begins to level out, and in a lot of cases will actually go up. There are a lot of examples where at some point you throw more and more processors at a given problem size and it'll actually run slower. And that's non-scalable algorithms. Weak scaling, on the other side, is the idea that I'm keeping my problem size per processor constant. And so as I add more and more processors to solve my problem, I'm growing the problem commensurate with that size. And the goal here is I have a bigger machine, I want to run a bigger problem in a constant amount of time. And so if you plotted that, here a weak scaling chart, ideal scaling would be something where the time is constant, because as I increase the number of processors, I'm increasing the problem size. The amount of work per processor, again, stays the same. Any overhead that I'm paying for like that message passing traffic is going to cause scaling curves to begin to look like this. But perfect scaling would be something that looks largely flat. The way these are usually represented in papers or in talks are, is speed up or parallel efficiency. Speed up, I think most people can probably grasp what that means. It's just basically a ratio of the time of one run to the time of, my run on more processors. So it's if I had one processor and I threw my problem at it and it took 100 seconds to run, now I try it on 16 processors, I got a 10x speed up. Pretty basic stuff. Parallel efficiency is a little bit easier way to wrap your head around speed up, because it's a measure as a percentage between 1 and 100% of how close we are to ideal speed up. It can actually go above 100% if you're getting what's called superscalar speed ups, but I won't go into that. And here it's usually, like I said, it's expressed as a percentage, and if we use the above example, I got a 10x speed up on 16 processors, I'm 62.5% parallel efficient. And again, you'll see people plot efficiency curves where usually 100% is ideal. And you can use parallel efficiency both for strong and weak scaling studies. If you're going to use efficiency for a weak scaling study, you'll usually want to, instead of talking about the total time of your problem, you'll probably want to normalize that to some unit of work. Grind time is a lot of finite element people talk about grind time, and that's the amount of time it takes to calculate one zone in one time step of your calculation, for example. So it's just normalizing the total runtime to take the total size of the problem out as a factor. And I just make a note here that the examples I used, I was saying we're calculating speed up based on one processor to some larger number of processors. It may be, especially in a strong scaling study where you're keeping the problem size the same, that you can't even fit that if you want to know how it runs on 10,000 processors, you couldn't even fit that on one processor because you just don't have enough memory in that one processor space, or it will just take, you know, all night or all week to complete. So a lot of times some of these scaling studies, you have to be careful to look where on the x-axis is 0. It may be that they started at, you know, 256 processors and are showing scaling out to, you know, 10,000 or whatever some larger number is. Amdahl's law. So this is another piece of computational theory that the first time you learn about it, you think, oh, why do we even bother with parallel computing? What it says is that your potential speed up that you're going to get out of doing things in parallel is going to be limited by how much parallelism you're able to express in your algorithm. Another way to say that is if you've got serial sections in your code, parts of your code that aren't parallelized, where everything has to be coordinated perhaps on one processor, that's going to limit the potential of your overall speed up. And this chart here shows that, you know, if you crank through this calculation here and plot this on a chart, you sort of very quickly asymptotically reach some scaling limit due to Amdahl's law. So what this is saying is, you know, my theoretical speed up, if I've got n processors, you know, n could be 16 or it could be 1,000, and 50% of my problem is parallel, well, the maximum speed up I can get, no matter how many processors I throw at it, is going to be about 2x. I mean, that makes sense, right? If p is 0.5, 50%, you know, you can do the math in your head here. That's going to come out to a factor of about 2. What's depressing here is that, you know, you can spend your lifetime parallelizing your code, get 95% of it parallelized, and you'll never achieve better than a 20x speed up, no matter how big a machine you've got. And, you know, as you get to 99%, well, there you reach about 90x. 99.9%, you know, 500x. So it's really all about making sure that every part of your application is able to run parallel. If you want to get scaling on these big machines like Titan and Mira, you have to be able to make sure you've got none of these serial sections. So back to our cartoon architecture here, I'm just going to touch briefly on this idea of programming models. And I've talked a little bit about this Mpi Message Passing, which is a library of calls to allow you to, you know, coordinate communication between processors across nodes. So back to our cartoon here, we've got a node with a number of processors and a network interface. Today, typically, this isn't the only way to do it, but typically people will use MPI to do that communication. And in fact, a lot of codes still use MPI to communicate between cores on the same node. Assuming you've got enough memory, that's actually not a bad way to do things. But as you begin to get more and more of these cores on a node, and the amount of memory isn't scaling as large, isn't growing as large as the number of cores you've got, you're going to start getting less and less memory per core. You'll hear people talk about the memory per core issue as being one reason that running MPI everywhere is becoming more difficult. Because again, an MPI task, if you think of it mapping to one of these cores or a node, the amount of memory it takes, it has to have everything it needs to perform its calculation, which may include things like what's called ghost elements. So these are elements that it just reads data from, that's communicated from other processors. So one way around this memory capacity problem is to use the shared memory model. And if you remember back to distributed versus shared memory, you know, all these processors on a node have a common address space here, and so that they can write and read to common addresses. And you can get parallelism through things like OpenMP or POSIX threads is a more low-level way to do this. But the idea here is that you use these directives in your code to express, I want this loop to run in parallel, and make sure that, you know, if there's a reduction at the end of the loop, maybe, you know, one scalar value where I'm summing everything, that's called a reduction, or I'm calculating the maximum value across an array of values. If there's some kind of reduction there, there might be a special pragma to say, you know, make sure multiple of these cores aren't trying to write to that same address space at the same time. And this is where you begin to get some of the overheads associated with shared memory, is in, you know, you have to lock these memory positions so only one core can access it at a time. And then more and more you're hearing people talk about GPUs and accelerators. And there you've got a couple different choices. CUDA is the NVIDIA model. And today is probably the best way to get the fastest performance out of an accelerator. OpenCL is a more open, vendor-neutral model. OpenMP, the latest version, the same OpenMP that you use to coordinate threads, has a accelerator model built into it now. We're just starting to see some compilers come out that have support for that. But that's a way of allowing you, just through these directives, which again aren't technically part of your source code, they're hints to the compiler as to how to structure things. But through these directives, you can say, for example, I want this loop to be offloaded and run on this accelerator. And here's the data that I need to give it, because I need to transfer data over to the memory space in that accelerator. And when it's done, here's the data that I need back on my CPU so I can continue the calculation there. And I'll talk about GPUs in a little bit more detail coming up. I've talked about vector processing. Vector processing isn't completely dead. As I mentioned, a lot of today's processors have much smaller vector widths, usually 4 wide data approaching 8. And that means, if you can load, 4 values in an array worth of data into one of these vector registers, or SIMD units, they're typically called, you can, calculate all of those in a single calculation. By the way, SIMD stands for single instruction, multiple data. That's when I say SIMD, I'm pronouncing SIMD. This is something called Flynn's taxonomy. It goes way back 20 or 30 years as a way to describe different ways to lay out parallelism. You can have MIMD, which are multiple instruction, multiple data, and various combinations. But typically, you'll hear people just talk about SIMD units, and just think in your head, these vector units where you're calculating a group of things all in one clock cycle. So this type of vector processing, we're just going to call this instruction level parallelism. And what I'm starting to hint at here is all the different levels of parallelism you need to think about to target these machines. So vectors are what we call instruction level parallelism. If you hear people talk about fine-grained parallelism, they're probably talking about threading using shared memory directives, or perhaps threads on an accelerator to accelerate their code. And then coarse-grained parallelism is usually this idea of message passing. And granularity here, fine-grained versus coarse-grained, it's really just how much work am I doing before I need to, for example, communicate or coordinate with other parallel units. And if today you really need to think about all these things simultaneously, and I've got a chart coming up that lays that out, and it's becoming more and more important for you to understand the impact on the underlying resources to get maximum performance out of your code. There's a couple emerging programming models that are starting to get more attention. I'm just going to touch on these very quickly, just so that you've heard the terminology and you know basically what they are. PGAS stands for Partitioned Global Array Space. So this is the idea that if I've got a distributed memory machine, where this idea of nodes that have an interconnect to communicate, this gives me the appearance that it's a common memory space, so that when I define my problem, I can just lay it out as one big array and index into things that may live on other processors. So it's really giving you all the programming benefits, the ease of programming of the shared memory model with all the hardware benefits of the distributed memory model, being able to scale your hardware out with the number of nodes. And so this is just pictorially shown here that under the covers, you've got physically distributed data, but the appearance to you is a global address space. And then communication is done through, basically a write into a global array. And it's up to some runtime system or the compiler to understand that, if I say I want to do a write to a sub I in my array, if that value of I, the index of that array, lives on another processor, will actually perform an underlying communication across the interconnect to put the data there. And there's languages like UPC, CoArray, Fortran, Titanium that support these models. Interestingly, Fortran, this is part of the Fortran standard now. I think it's the Fortran 2008 standard. So people like to bash Fortran for being this old dinosaur language, but it's actually far ahead in adopting some of these parallel features into the base language. Another programming model is this idea of task-based or event-driven. The idea here is if you can express your problem as a number of independent tasks and just say, for this task to run, I need this data as input, and when my task is done, I'll provide this data as output. If you can express your program like that, you'll come up with some sort of graph like this that then some underlying runtime system can go ahead and figure out how and when to schedule these tasks dynamically. And so Charm++ is based on this model. HPX, OCR is the Open Community Runtime. It's an emerging library coming out of some of the XStack work in DOE. So again, that's all I'm going to say about these models. If you're interested in these, there's plenty of papers and discussions out there. While I'm still on terminology, I want to talk a little bit about Moore's Law and really more importantly, Dennard scaling. So everybody's probably heard of Moore's Law, the idea that, if you just read about it in the paper, it's computers get twice as fast every 18 months or something like that. What Moore's Law really says is that the number of transistors will double about every 18 to 24 months, which historically has translated into computers getting faster. But that's no longer happening, and that's due to something called Dennard scaling. Robert Dennard was an IBM researcher, best known for inventing DRAM, which is dynamic random access memory, the standard memory that we use in pretty much any computer these days. But he also came up with a set of, a theory and a set of equations that stated that the power density on these chips per transistor would remain constant. And this is starting to get a little bit in the weeds, so I won't spend too much time on this. But basically, as transistors were shrinking, which is what Moore's Law said would happen, so would the voltage required to run them, and the power density for a given area on a piece of silicon would remain about the same. Well, back in about 2005, 2006, Dennard scaling broke down due to something called thermal runaway. In a nutshell, you couldn't keep cranking the clock rates up on your CPUs to get better and better performance. If you remember, back in the late 90s, 2000s, getting a faster computer meant going from my 2.1 gigahertz machine to my 2.8 gigahertz machine. Clock rates were going up and up. That eventually is leveled off, and it's because of this Dennard scaling. So, really what will happen is if you keep cranking your clock rate up, you've got so much heat on the chip that it'll melt itself, and then it's not really good for anybody. So this chart here, this is a little bit out of date, but this tries to capture in a nutshell what that means. So this green line here, this is Moore's Law, and Moore's Law lives on. The number of transistors continues to double. Everything's going as expected. By the way, Moore's Law probably has a lifetime of another 7 to 10 years at most, so we are going to run into that. But what has happened in the meantime, and this is a blow up of what these different colored lines mean, is that because of this Dennard scaling issue, the amount of power that we put into a chip began to level off. The clock speed has begun to level off, and as a result, the amount of performance that you can get out of any single instruction in a core has leveled off. Yet the number of transistors on it that you can put in a given area continues to go up. So what do we do with those? Make separate cores, right? So this is what has driven the multi-core architectures that you see now in everything from supercomputers down to cell phones. That you can't make computers or chips any faster by cranking up the clock rates. What you need to do is add more cores, put them in the same amount of area, and then leave it up to us, the programmers, to figure out how to make use of that parallelism. So parallelism is something that's beginning to pervade the entire industry, not just HPC. Memory systems are getting increasingly complex. It used to be, well, today you've got a CPU with some amount of cache and a main memory and then disk. What we're beginning to see is that the speed of memory has not been growing as quickly as the compute speed has. So we've run into this what's called the memory wall. Basically, you can't feed the processor enough data fast enough for it to run its fully efficient speed. We're hitting a one-time nice bump here where we'll have something called 3D stacked memory that will help with that. And DRAM, due to power constraints, will probably be replaced by something called NVRAM, non-volatile RAM. Think of flash memory, for example. So bottom line, memory systems are going to get increasingly complex. And I'm running low on time, so I'm going to go through these last bit of slides pretty quickly here. But this is an example of a stacked memory technology called the hybrid memory cube that Micron has been developing. And in addition to being just faster memory, which is a nice trait that we need, there's also the possibility of putting actually a small processor there close to memory. So now you're going to start seeing a model called processing in memory emerging, where instead, if I want to do a calculation, instead of saying, give me this value and give me this other value, and I'll add them together, you can just ask the memory system, give me the sum of these two values. And some simple computations could be done out there, for example. So Hpc Node Architectures, this is, I'm just going to summarize a couple things I've said. They used to be simple. You had a CPU with memory. We've gone to this multi-core architecture. We've seen things like accelerators that have typically been on these slow buses, so you had to have a lot of work offloaded to your GPU to pay for the amount of time it took you to get your data off into that separate memory space. What we're starting to see now, and this is in the new CUDA, CUDA 6, I think it is that you'll have a unified memory space between your CPU and your architecture. It's going to make it easier on the programmer because you don't have to explicitly move data back and forth to the accelerator unless you want performance. Then you're probably still going to have to move some data around explicitly. This idea of stacked memory, and this is just a reflection of the last slide I showed, that you may have these big multi-core CPUs with 50 or 100 cores on them. Some small amount of fast memory, but that fast memory may be too expensive to use in its entirety, so you'll back that up with some slower memory on a slower bus, and now you have to think about how do I manage these multiple memory hierarchies. And then finally, this idea of processing in memory, where I may have a CPU that has some small amount of computation available out there in memory space. The thing we're struggling with is that we need a programming model that lets us attack all of these things, so that we don't have to have different versions of our source code for all these different architectures. And then real quick, this is just an example, going the various levels of parallelism, again, just kind of summarizing what I've talked about. We've got message passing in between nodes. You've got shared memory where cores on a node can communicate through memory space. I haven't talked about hardware threads yet. Let me just briefly, I'll probably run over a minute or two, but this is an important point because hardware threads you're going to start to see more and more. They're on the Blue Gene machines. The Intel Mike architecture, or Xeon Phi, is going to have hardware threads. If you look at complex CPUs like the x86 Xeon, there's a lot of silicon on that chip that's doing some magic under the covers for you, so that, for example, if an instruction gets executed and it decides it has to go all the way out to main memory to get a value before it can continue, instead of maybe getting a value quickly from cache, that hardware has a lot of logic built into it to automatically reorder things on the fly for you. And while that instruction is waiting for that memory fetch to come back, it can go ahead and calculate some other things. This has been why these fat core CPUs that you'll hear people talk about have been so performant that they take a lot of the burden off the programmer. Well, as these power constraints and we're building simpler and smaller and lighter weight cores, what hardware threads do is basically put that burden back on you, the programmer. Again, to tell the hardware where the concurrency is in your program, so that if I've got a hardware thread running on a core and it hits a memory stall, it can very quickly, usually in one cycle, switch to the next thread of control in your program. And so that by the time all those threads are done executing and it comes back and executes that first hardware thread waiting on the memory stall, the memory is there. And so it's really a way to hide this memory latency, the idea that you can wait for a long time for things to come back from memory. And then each of these hardware threads may be targeting vector units. So burst buffers, really just a way to decrease the amount of time we spend doing checkpoints. So usually you're running an application and you want to write a restart file, for example, the state of your program out to disk. Things come to a screeching halt today while you're waiting for things to go out to the spinning disk. The idea of a burst buffer is essentially to put some level of non-volatile memory on your system. You can quickly write to that. Think of it as either slow memory or a fast disk. Quickly write to that, let it buffer it, go back, let your calculation continue, and then the system will trickle that off to spinning disk as needed. So that's the idea behind a burst buffer. I'll skip some of these. Resilience and fault tolerance is a big issue. This could be a whole hour-long talk on itself just to talk about the different taxonomies for resilience here. I'm going to skip through these. This is just saying that it's not just hardware that needs to think about scalability. It's not just applications. It's also things like tools, debuggers, performance analysis. All of these things are challenges as we get to this more and more parallelism that we need to start pounding those nails down. And then finally, big data, data science. It's the buzzword of the decade. And there's really a merger coming between HPC and data science. We have data science challenges in high performance computing, ranging from problem setup to machine learning techniques to uncertainty quantification, doing things in situ instead of writing them out to disk and post-processing. So if you're interested in data science, there's a role for you in HPC as well. And then finally, I just wanted to mention co-design. I think this is my last content slide. Co-design is this, DOE has these co-design centers that are set up. They've been running now for about 3 years. The idea here is that we want the hardware developers developing this next generation of machines to be informed by the needs of the application programmer and vice versa. We want the application programmers to understand what the long-term roadmaps are for these architectures and have some influence on that. And there's a couple programs in DOE going on called Fast Forward and Design Forward to attack this. So this really is my last slide. So it's an exciting time to be in HPC is the bottom line. And this is just summarizing some of the things I've said that, whereas we used to tune algorithms to reduce the amount of flops or floating point operations, now we're tuning algorithms to reduce the amount of data motion. We have to think about heterogeneity and a lot more concurrency. These non-uniform memory access architectures, power management, there's a whole range of challenges, all of which together make up this exascale problem that you'll hear a lot of people in DOE talking about. So there, now I really am done. A little bit over time, but thanks for your attention. And again, if you have questions, I may have to ask Britton to repeat them because I'm a bit deaf, but I'm happy to take any questions, or you can grab me at the break.